So we're going to think today about lines and circles. And as always, I hope my ideas, I hope they appeal to you, I hope they interest you. And I hope you think, oh, yes, I could use that in school. I could use that. And of course, now you could think that literally in school. I mean, it has been good this week. A bit of sunshine, a bit of warmth. And when I went to take the bins out the other day, I noticed the crocuses in the pots by my front door start to come through. So that was lovely. And of course, the good news about schools. I mean, obviously, getting kids back into school is going to be difficult. But I do think it's a good place. It's the better place. It's the best place for them to be. So I'm conscious we've got some difficult couple of weeks. Well, not difficult, a few months ahead, but particularly the next couple of weeks are really going to be really difficult. I know my thoughts are with you and your colleagues as you make that happen. So when we're actually back in school, hopefully some of these ideas might work well in the classroom. Why did I choose this topic? I mean, essentially, it's coordinate geometry, lines and circles, coordinate geometry. And I chose it because I think it's a really good example of where fluency and understanding come together. So any question about coordinate geometry would involve maybe finding where two lines meet, solving simultaneous equations, finding where a line and a circle meet, solving a linear and a quadratic simultaneous equation. So it's going to involve lots of fluency, lots of algebra skills. But also there's the interpreting of those answers. So, in a very simple case, when you solve two linear simultaneous equations, what you're finding is that are the coordinates where those two lines would intersect. And of course, if the lines were parallel, then they wouldn't intersect, or they'd be identical. They'd either be utterly distinct or utterly identical. So what would that look like in the simultaneous equations? How would we know that in the simultaneous equations? And I think there's a very strong interplay between fluency, doing the algebra, getting the answer, and understanding what the answer is telling us in the geometrical context. And that's why I think it's really important to link these two together. And I think this topic does it. And those of you who teach Key Stage 5, or those of you who think back to your own Key Stage 5 experience, will know this is so important at A-level, particularly in further maths. So hopefully some of your students at least will go on and study, so hopefully all of them will go on and study maths in your top sets in year 11. Hopefully quite a few of them will go and do further maths as well. And this idea, they come back to in further maths again and again, the idea that algebra and geometry being sort of two sides of the same coin. They're saying the same thing, they're just speaking it in different languages. And therefore getting that idea, sowing that idea now is really laying the foundations for future success in Key Stage 5. And that's really what motivated me to choose this topic. It is this whole idea of linking together the how and the why. We want our students to become fluent, to develop techniques, to be able to record and apply knowledge. We want them to solve problems, and we want them to be able to express and articulate their mathematical reasoning. And I think this topic is a really good context for doing so, e.g. the following. So here you are, a little thing for you to think about for, I don't know, three or 4 minutes maybe. So choose 4 coordinates that make a quadrilateral, work out the midpoints, join them up. Then make a new quadrilateral. Don't iterate again. Don't sort of do it again and again and again on the same quadrilateral. So you sort of choose a quadrilateral, take the midpoints, and you join them up and have a think. Okay. Then make a different quadrilateral, and take the midpoints and join them up and have a think. And put some numbers on. Do some coordinates. So actually find out the values of the coordinates and the midpoints and the sides, and then that will give you an idea of what maybe is going on here. So I'm going to leave you to do that. I'm going to do an example myself on the screen. And whilst you're doing it, of course, be thinking about why. Why would this be useful in the class? Why would you set this question? What would you get out from this question? How would this question develop reasoning, problem solving, and fluency? What should we have? Any first thoughts from your own diagram or from my diagram? So I chose fairly random coordinates. There was a little bit of rationale behind them. Certainly, my original shape, my orange shape, is not anything in particular. It's not a special quadrilateral. It's not a trapezium or a rectangle or anything. So, any observations either from my shape or from your own shape about what you've made, what's happened with the midpoints? Oh, so when you say then a rectangle, is that clear because you've done it again? Have you then done the same thing but in the center of so you've made the inner shape, and then have you found the inner of the inner shape? Is that, are you sort of doing it twice? Is that why they keep ending up? Yeah. Okay. Well, let's take a step back. Let's just look at the first shape. Keep it ending up with a rhombus. Okay. So Claire's got a rhombus. Anyone else got anything familiar? Any more rhombuses? Rhombus? No. Any more shapes coming? Have I got a rhombus? How can I think about that? Okay, so if I give some I'm going to call these I don't know, P, Q, R, and S. So I'm going to think about the vector PQ, think about the journey from P to Q. So -5 to 1 is across 6, -1 to 0 is 1. And then I've got Q to R. So Q to R is 5 to 7, which is 2. And no, sorry, it's 1 to 7. 1 to 7, which is 6. And 0 to -4, which is -4. And then P to S, the vector P to S is -5 to 1 is 6, and -1 to -5 is also -4. And then S to R is from 1 to 7, which is across 6, and from -5 to -4, which is up 1. Okay, so I've got a parallelogram, not a rhombus. Okay, it'd be interesting to know. Wonder what shapes you started with. So I was not expecting to get a rhombus. I was expecting to get a parallelogram. Okay, because that is what happens. And that's what I've got. I've got a parallelogram, not a rhombus, because these lengths are not the same. The side lengths are not the same size. Okay, but interestingly, it's the fact that we've got either a rhombus or a parallelogram. So having started off with just any odd quadrilateral, we've now got a shape which has got quite specific properties, i.e., it's got two parallel sides, and well, for Candice and Charlotte and Claire. So Claire, because you start off with symmetrical shape. So that's okay. Well, straight away we've got a conjecture. We've got a thing happening in the classroom. Why did you get a rhombus? Well, maybe because we start off with something symmetrical. May well be. So what we've got is we were generating from a non-specific, from a sort of a random quadrilateral, an unstructured quadrilateral. We're generating an inner shape with sorry, I just lost my sorry. This is going to look very bad on the recording because you can't see the chat. Whereas, so someone's just put in the chat, oops. Sorry, complete train of thought lost there. Right, okay. So not a rhombus, Charlotte, after all. Okay, so we start off with an unstructured quadrilateral, and then what we've ended up with is a very structured quadrilateral in the center, a parallelogram or possibly a rhombus. Now, does this always happen? Answer yes, but of course, what you want the students to be doing is thinking about, well, why is that the case? How can we prove it? How might we go about exploring this? Why is that so? But even taking a step back, why is this a good activity? Well, actually, because we're doing quite a lot of fluency. We're doing the whole fluency about midpoints, aren't we? So how do students work out midpoints? Well, if I just jump ahead to question where I've asked this. Yeah. So here's a triangle. So if I've got a triangle with vertices at -6. By the way, when I'm drawing shapes, when I'm drawing coordinates like this, I'm trying to draw them not on, obviously not on graph paper, obviously not to literal scale, but I'm trying to draw them relatively sensibly, relatively placed sensible to each other, and that's a really good discipline to expect and develop in your students. So obviously -2, 4 is to the right of and below -6, 6, and it's to the right of and above -3, 1. So I'm trying to draw them not in proportion, obviously, but with a sense of proportionality, with a sense of scale, with a sense of where they are relative to each other. Okay, so how do you find the midpoint? Well, the fluent way is to add the x coordinates average, add the y coordinates average. So -6 and -2 makes -8, half of that is -4, 6 and 4 is 10, half of that is 5. -6 and -3 is -9, so -4.5, 6 and 1 is 7, so 3.5, and then -3 and -2 is -5, so -2.5, and 1 and 4 is 5. So that's the fluency. You want them to have that at their fingertips. How do I work out the coordinates of the midpoint? I add the x coordinates and find their average, add the y coordinates, find their average. The trouble with that is that it doesn't generalize to points of trisection. 2.5, not 5. Thank you. Yes, thank you, Stuart. So 4 and 1 makes 5, and then divide by 2, so it's 2.5. Thank you. Obviously, it's not 5 because 5 is not between 1 and 4. Thank you. Remember to divide by 2. Thanks, Doug. I see what you meant now. This doesn't generalize, it doesn't extend to points of trisection, to points in the ratio 3:2. So you do need to check, can they also give an alternative argument? And probably the best way to do it is the vector argument. So what do we know about that vector? So it's across 8 down 2. And so that vector is across 4 down 1. So it's across 4 from, -6 and -2 is across, -6 and -2 is across 4, not across 8. So it's across 2 from -6, so that takes us to -4, and it's down 1 from 6, which takes us to 5. And of course, that argument does generalize. That argument, I could do the point quarter of the way along, or a third of the way along, or say in the ratio 3:2. So if you remember, one of my principles about getting the maths from them is give me another method, give me another reason, give me another explanation. I think this is a really good example of it. Give me a way of working out the midpoint, average the coordinates. Give me another way of working out the midpoint, start at one point and move by half the translation to the other point. And of course, those are different arguments. And then of course, you need to show, do they always give the same answer? And that's where perhaps a bit of algebra comes in. So I think a task like this, or an activity like this, is great because it draws out the fluency of working out midpoints, the reasoning of how they work out midpoints, plus all the reasoning about, well, are these parallel? Are these equal length? This is a parallelogram, this is a rhombus, etc., etc., etc. So I would use something like this at the beginning of a unit, a block of lessons on coordinate geometry, because I want to find out what they can do. I want to find out what they can remember, what procedures they've got at their fingertips, or perhaps not at their fingertips, perhaps somewhere high up in their arms, and they need to be brought out to their fingertips. And I also want to know what reasoning skills they can apply once they've followed the procedures through. Can they interpret what they've done? So as we've begun, we're going to think about quadrilaterals and triangles. We're going to do a bit more work on triangles and quadrilaterals, and then we're going to think about triangles and circles and lines, and then a trailer that we're going to pick up next week with circles and circles, because sort of the overall topic for the last week is circles and angles, i.e. circle theorems. But there's a very nice bridge from circles and lines to circles and circles, or circles and angles and circle theorems. And you might even predict what that bridge is going to be. So there's going to be a bit of a cliffhanger ending at the end of this week, and hopefully you'll come back next week for the final instalment. And I think it's just a really good example of that quotation I've used with you before from Gattegno. Teach the little that leads to a lot. The little is basically solving algebraic equations. The lot is all the geometric interpretation that's going to come from it. So again, finding out what do they know, what do they think, what do they recognize. Here are 3 sets of coordinates. What can you tell me about these triangles? So I'll give you a couple of minutes to have a play. Again, you might want to draw them. You might want to draw out some, to think about what can you see, what can you conjecture, what can you verify. So here are some triangles. What do we notice? So I'm going to try and draw them, and again, I'm going to try and draw them sort of with a degree of sort of relative accuracy. So 6, 13 is kind of all the way up there. And then 19, -3 is going to be kind of like down there or sort of something. Where is that one? So that's one. So I'm sort of thinking something like that, maybe. And again, I'm trying to draw them with a sense of their position relative to each other. I basically left, right, above or below. So 3, -8 is below 1, 6, but also it's below -9, -4. So hence I've drawn it down there. Thoughts, observations? Oh, okay, Charlotte. First one, is it right angled? Well, it kind of looks like it might be because of the way I've drawn it. So great question. Is it right angled? How might we go about finding that? Well, this is what we're trying to find out from our year 11s. Hopefully, fingers crossed, somebody will say gradients. So, okay, let's think about gradients. So what is the gradient? That is up 12 across 3. Yeah, so from 1 to 13 is up 12, from 3 to 6 is across 3. So that's got a gradient of 4. And then what about this here? Well, that's gone down 4, from 1 to -3 is down 4, and it's across 16, from 3 to 19 is across 16. So what's the gradient there? Well, it's 4 over 16, it's 1 over 4. Oh no, it's not, it's negative, so it's -1/4. Ah, that looks encouraging. That looks very encouraging. So it's 4 times -1/4, which is -1. So the gradient's multiplied by -1, so it is indeed a right angle triangle. Ah, and then Charlotte separately suggests in the chat, thinking about length, thinking about dimensions, thinking about therefore thinking about Pythagoras. That's great, Charlotte. Actually, that's what I'm going to do on the next slide. so great minds think alike. That's coming up on the next. So hold that thought in the chat. We'll come back to that in a moment. So gradients is one way of doing it, but also we could think about by Pythagoras. But I want to come to that in a moment for a reason which will become clear. So yes, this is a right angle triangle, and a nice way of showing it is to think about the gradients and making sure that our students remember that if they multiply by -1, if one gradient is the negative reciprocal of the other gradient, then the two lines are perpendicular. What about the red triangle? Is the red triangle right angled as well? Well, let's do the same thing. It worked once, let's do it again. So what have we got here? We've got up 10 across 10. From -9 to 1, -4 to 6. Here we've got across 2 down 14. Well, that's not a right angle. That is definitely not a right angle across 2 down 14. Sorry, that's not a right angle with 10, 10 because the gradients are so different. And then what about here? Here we have got across 12 and down 4. So we've got gradient 1, gradient -7, and gradient -1/3. So okay, so that one is not a right angle triangle. It is something though. Can we want to suggest what it is? It isn't right angled, but it is something. It's so is it equilateral? That's a bold claim. It might not be equilateral. It might be isosceles. So let's find out. So 10 and 10. So 10 and 10 make 200. So root 200. Sorry, 10 and 10 make 100. 100 make 100. So square root of 200. 4 and 12. So it's 144 plus 16, which is 160. Oh right. So it's definitely not equilateral. It's definitely not equilateral. It's root 160. And then 2 and 14 is 4 and 196. So that's also 200. So that's root 200. So it's isosceles. It's an isosceles triangle. So it's root 200, and it's root 160. It's an isosceles triangle. And thoughts about the third one? Any thoughts about the third one? This is where my drawing has, as it were, let me down. Any thoughts about the third one? So let's think about isosceles. Okay, so let's work out the thanks, Stuart. So let's work out the dimensions. So -3, that's going to be across 5 up 5. Yeah. So -3 to 2 is 5. -1 to 4 is 5. What about this one here? So -8 to -3 is 5. -6 to -1 is also 5. Okay. So that's kind of looking plausibly isosceles because they're the same length, but something's bothering me here. Something should be bothering me here because hang on, they're the same length, but also they're the same gradient. So yes, 5 and 5. So 5 and 5 and 5 and 5 will make the same length, but actually this is deliberately not a very good picture because actually it's not just the same length; they're the same gradient. So really, the picture is -8, -6. Then -3, -1, then 2, 4. Those two line segments have got the same gradient. It's not a triangle. They've got the same gradient, so they're parallel, and they've got a point in common. So they're going in the same direction. The end of one is the beginning of the other. No, you've not made a silly mistake, Helen. First of all, there's no such thing as silly mistakes. Okay, there are sometimes avoidable mistakes, but they're not silly mistakes. But it is a straight line. It's exactly so. I made this to be a straight line, and I drew it deliberately, unfairly. I drew it to look like a triangle. So it's a straight line because they've got the same gradient, and it looks like it's isosceles because it's got the same triangle, but because they've got the same 5, 5 triangle, but because it's got the 5, 5 triangle, actually the same gradient, and so these line segments are parallel with a point in common, i.e. the 3 points are collinear. And if you look at the sort of the 2 points that are far away, you can see it's across 10 up 10. So how do you go across 10 up 10 with 2 steps of across 5 up 5 across 5 up 5? They're all in a straight line. It's all a straight line. These are 3 collinear points. They've got the same gradient. So it's not a triangle. Okay, that means we can now think about the area of the triangle. So if we go back to the one we had a moment ago, we know it's a right angled triangle, and so we know it's we're going to use half base times height. So let's use that as the height, and let's use that as the base. Now let's work out some lengths, and from the 12 and the 3, so 12 is 1 squared, 1 for 4, 3 squared is 9. So that gives us here a length of 153 because it was 12 squared and 9 and 3 squared. And then here it was 4 squared and 16 squared, so it's 256 and it's 16, so it's 272. So the area is a half of root 153. The area is a half of root 153 times by root 272. And so the kids do that in their calculator, and then OMG, they get the exact answer, 84. So why on earth has it got the exact answer, 84? And this is exactly 102. Yes, 102, not 84. 102. Sorry, Charlotte. Thank you, Charlotte. 102. Okay, and why is it exact answer? Why is it 102, not a third answer? Well, this is what Charlotte was saying in the chat earlier. That what we've got here is this is a 12-3 triangle. So really, it's a 1-4 triangle scaled up. So really, it's a 1-4 triangle with therefore hypotenuse root 17 scaled up 3 times. Here, we've got a 4-16 triangle. So again, we've got a 4-1 triangle with hypotenuse root 17 scaled up 4 times. So therefore, this has got to be a 3-4-5 right angle triangle, so by Pythagoras. But in terms of the area, what we've got 3 root 17, we've got 4 root 17 and a half of that. So altogether, we've got 6 lots of 17, which is indeed 102, not 84. Now, why has that happened? Is that just a coincidence? No, because if you think about these being perpendicular, if this one is going to be a 1-4 gradient triangle, then to be perpendicular, this has got to be a 4-1, or suppose strictly speaking, a 4-1. You've got to rotate the little green triangle appropriately, actually reflect first and then rotate. So you've got, so the gradient has got the negative reciprocal. This wouldn't work. They wouldn't be perpendicular if that was a 1-4 triangle and the next one was say a 5-2 triangle or a 6-7-3 triangle. That wouldn't work because they wouldn't have gradients of 1/4 and 4/1 or negative 4/1. So to be perpendicular, you're going to necessarily get these two congruent but rotated, these two congruent triangles, and therefore you are going to get this fact that you've got the same triangle but different scale factors, i.e. the third part, the third hypotenuse, is going to appear in both the triangles, and so when you multiply them together, you're going to get a whole number answer. And then similarly for the isosceles triangle, well, obviously what we do with isosceles triangles, we split down the middle, and so making sure they split it down the middle and then work out the height and the base from that. And I suppose they could work out the midpoint, but they don't need to, because with Pythagoras, of course, they can work out, if they've got the side length and the base length, half the base length, they can work out the height of the triangle overall. So this is basically the same question, but what's harder here is I haven't given the coordinates. So same idea, let's draw it. So 2y is 3x to 5, so what's that? That's a sort of positive gradient, relatively steep. What's that? 7y is 4x to 50, that's also a positive gradient, but nowhere near as steep. And then what's that? 3y negative, so that's a negative gradient, so kind of something like that, maybe. Right, so where do these lines intersect? Well, that's just simultaneous equations. So what I might do then is say change that into, let's make it 6y is 9x subtract 15, and then let's make that one into 6y is negative 4x plus 24. And then let's subtract them. So I get 0 is 9x subtract negative 4x, which is 13x, and then negative 15 subtract 24 is negative 39, and so x is 3. And then y will be, in the orange equation, 3 3 is 9, take away 5 is 4, and divide by 2 is 2. So that's the point 32, and then I can find the others. And then exactly, Claire, the question is, are the purple and the orange perpendicular? And wouldn't it be great if they were? Because then that would give me a right angle triangle. So are they perpendicular? Yes, because that's got gradient 3/2, and that's got gradient negative 2/3, and so therefore they are indeed right angle triangles. And so I've got my right angle triangles. So now when I do the area, I want to make that say the base and that the height. The base doesn't have to be the base. The base doesn't have to be the bottom of the triangle. The key thing is the base and the height are perpendicular, are at right angles to each other. So if that's what my triangle looks like, make that the base and make that the height. There's no reason for the base and the height to be, well, certainly for the base to be the bottom of the triangle. And that's the point of this question, is to really emphasize that to the students. You see it lots. You see questions like this, where they have to work out like a pennant flag area, or something like that. That's vertical, and they start faffing around with trying to work out what that is, and trying to work out what are you doing? What are you doing? That's the base, that's the height. Job done. So it's a very entrenched belief that the base has to be the base, and the whole point of this activity is to stop them doing it. Okay, let's step up quadrilaterals. Right, what have I got here? Well, here I've got parallels, but I haven't got perpendiculars. So I've got some quite steep lines of gradient 7, and some quite shallow lines of gradient 7th, but they're not perpendiculars. So what have I got? Well, I've either got a parallelogram or a rhombus. And so same old, but we'll work out the intersection points, solving these simultaneously. And yeah, these are not nice numbers, so there's lots of good arithmetic practice, lots of good algebra practice, that fluency. So I can't snap my fingers. I'm just rubbing my hands slightly weirdly, rubbing my hands with glee. It should be at their fingertips. So you want them to be able to work these things out pretty quickly, you know, ideally without a calculator. So they'll get the coordinates, and then the question is, you know, what's that length there? What's that length there? What's that length there? What's that length there? Have we got a quadrilateral or have we got a rhombus? Sorry, have we got a parallelogram or rhombus? And then, sorry, Claire, are you talking about this question or the previous question? Sorry, Claire, which question? I just looked at the chat. You're talking about this one or the previous one? This one, yeah. So absolutely. So what do we do with this shape? Well, splitting is a good idea. And actually, if it's a rhombus, then because these lines are all equal and the angles are opposite angles are equal, everything must be symmetrical. So the diagonals, obviously it's not true for parallelogram. For a parallelogram, the diagonal is not a line of symmetry, but for a rhombus, the diagonal is a line of symmetry. And therefore, that must be a right angle. These must be right angles in the middle. Because if you've got symmetrical angles adding up to 180, they've both got to be 90. And so we can either make two isosceles triangles and split in half, or we can make 4 right angle triangles. Either way, working out the area of a rhombus is much easier than working out the area of a parallelogram. So I'd highly recommend, hoping, fingers crossed, that I've designed a question which has got a rhombus on it, and if you make up your own question like this, I would make it a rhombus because it makes the calculation easier towards the end. Okay, so midpoints. So if we start with the vertices, we can work out the midpoints. What about the other way around? It's just a really simple idea. Just go backwards. What about if I tell you what the midpoints are? What are the vertices? So if I have the midpoint -6, 6, and then I want -3, 1, and then -2, 4. So same coordinates as on the previous slide, but now these are the midpoints. So what does the triangle look like? Well, if this is a midpoint, then I'm going to have a side kind of going through -6, 6, but also a side going through -2, 4. And they're going to meet somewhere sort of like up there. So, and then sort of, if that was halfway, then, well, it'll kind of do. That's a bit, well, I mean, that's a bit short. It's not really halfway, but it's kind of close-ish. You know, it's a sketch. I'm not trying to draw it accurately. But yeah, that is a good reasoning to go through for the students to experience. Kind of what does it, even just working out what the diagram looks like is a good activity. Right, so how are we going to find the coordinates of the midpoints? Well, there's got a number of ways of doing it. There is a sort of a brute force way of doing it, an algebra way of doing it, which has got a nice aspect to it. So although I don't think it's the most elegant way of doing it, I do think it's worth doing. You know, so what do we do with things we don't know? In maths, when we don't know something, we could call it a letter. So let's call this A, and then maybe P, and then B, and maybe Q, and then C, and maybe R. And just that step of algebratizing the problem. You know, I don't know what the coordinates are. It's an unknown number. How can I represent unknown numbers? I can use letters. That is hard, and therefore it's worth doing. That is productive struggle to get your Key Stage 4 top sets to be thinking about. That's the step to make. Why is that useful? Well, then I know that if I averaged A and B, I'd get -2. And so A and B by themselves, unaveraged, must make -4. And if I average B and C, I'll get -3. And so B and C by themselves must make -6. And if I average A and C, I'll get -12. And so A and C by themselves must make -12. Now what can I do? I've got 3 equations in 3 unknowns. You know, that's hard. What do I do? Well, what I could do is I could combine those 2 by subtraction, and therefore say maybe that A subtract C is -4 subtract -6, so that's 2. And then I've got A plus C is -12. So then I can add those together. If I add those together, I will get A and -C and positive C, i.e. no C's. So I'll get 2A is -10. So I'll get A is -5. I want to know what A is, and I can get what B is. I want to know what B is, I can then get what C is. So I can sort of chase it round from there. Alternatively, though, and I'm not expecting the students to kind of realise this, so you probably will need to show them this or draw it out through quite careful questioning. Really nicely is just to add all 3 of them together. Seems a bit odd, but anyway. So if you do that, you get 2A and 2B and 2C. So you get 2A and 2B and 2C is -4 and -6 and -12, which is -22. And therefore A and B and C by themselves are -11. Now that does not seem like progress. I now seem to have one equation with 3 unknowns in it. except that if I know that a plus b plus c is negative 11, and I know that a plus b is negative 4, then I know what c is. Then I know with no effort whatsoever that c must be negative 7. And if I know that a plus b plus c is negative 11, and say b plus c is negative 6, then I know that a has got to be negative 5, which we said earlier. And a plus b plus c is negative 11, and a plus c is negative 12. And so I know that b has got to be negative 1 to work with the negative 11 to make altogether to make positive 1, positive 1, because a plus c makes negative 12, and so b has got to be positive 1 to turn negative 12 into negative 11. And so the idea of combining them together, and it works because of the structure of the equation. In fact, it's a plus b, b plus c, actually even better, a plus b, b plus c, c plus a. So you've got what's called cyclic symmetry. As you rotate through a, b, and c, you just get the same equation, same structure of equation again and again. And adding them together preserves that symmetry, keeps that symmetry. A and b and c is the same as b and c, and a is the same as c and a and b. So kind of that cyclicity is preserved. And that's why it works. So that's quite a nice way of doing it. There are better ways of doing it. There's a geometrical way of doing it, and I will pick that up next week because it'll time with our work on angles. So there's a way. There's probably a better, more elegant geometrical way of doing it, but that will require us to think a bit more about angles, which I want to come back to in a week's time. So a trailer for next week. Triangles and lines have lots and lots of lovely properties. So, for example, let's take this triangle. It's got vertices at -1, -6, 5, 6, and 11, -2. That's my triangle. Now, the median, the definition of the median is a line which goes from the vertex to the midpoint of the opposite side. So the median goes from there to there, maybe at right angles, but not necessarily. Okay, it might hit it at right angles, but it not necessarily. But there's no reason why it has to. That's the midpoint. That's the midpoint, and it may or may not do so at right angles. So the question is, where is there? Where is the center? Where is the middle? So how are we going to do that? Well, let's find out where these coordinates actually are. So 5 and 11 makes 18 divided by 2. Sorry, 16 divided by 2 is 8, and 6 and -2 makes 4 divided by 2 is 2. And then -1 and 5 makes 4 divided by 2 is 2, and -6 and 6 makes 0 divided by 2 is 0. Okay, so that's where the midpoints are. So let's find the equations. So equation of a line, y equals mx plus c. So let's find the m. So what's the m? I've got across 9 up 8. So the gradient is 8/9. So the natural thing to do is write y equals 8/9 of x plus c. But then you've got the horrible fraction. And then if you multiply both sides by 9, you're going to get 9y is 8x plus 9c. So I don't. I write 8/9 of x plus something blob. Something mysterious. And then when I multiply both sides by 9, I get 9y 8x plus, and I just call it a different box. I know it's 9 times the previous box, but I don't really care about that. All I care about is it's just another number. And having integer coordinates is just so much nicer than having fractional coordinates. And coefficients. Having integer coefficients is so much nicer than having fractional coefficients. So I strongly recommend moving away from just sort of autopilot y equals mx plus c to y equals mx plus something, clear out the fractions, and then start thinking what something is. So let's use the coordinates to do that. So 8, 2. So 9y is going to be 18. So 18 is 64 plus watt. And so the watt is going to be 46. Yep. Sorry, -46. So altogether I get 9y is 8x subtract 46. Here, on the other side, so what's my gradient? I've gone across 9 down 2. I've gone across 9 down 2. So it's y is -2/9 of x plus something. Again, multiply through by 9. So 9y is negative 2x plus something else. I know it's 9 times the previous box, but I didn't care what was in that box. I don't really care what was in this box. All I know is it's a box. It's a number. Use the coefficient, use the coordinate, sorry, 2, 0. So 9 zeros are 0. Oh, that's handy. Take 2x, it'll be negative 4. So altogether, I'm going to have 9y is negative 2x plus 4. So those are my two equations. So where do they intersect? Where is that point in the center? So let's just get rid of the working. And concentrate on just the equation. So we had 9y is 8x subtract 46, and we had 9y is negative 2x subtract plus 4. So if we subtract those, we're going to get 0 is 10x subtract 50, and so x is 5. So that's got x coordinate 5, and then the y coordinate, 5 times negative 2 is negative 10, plus 4 is negative 6, divided by 9, so is negative 6/9, or negative 2/3. So they meet at the point 5, negative 2/3. Now, what's wonderful is that that point is also on the third median. Is it? Why is that? Where is the third median? So the third median is going from there. And where is that point? Sorry, that's not quite so well drawn. So where is that point? So negative 1 to 11 is 10, divided by 2 is 5, and negative 6 and negative 2 is negative 8, divided by 2 is negative 4. So it's on that line. What's that line? Well, let's find the gradient. Oh, the gradient is 10 over 0. Oh, crikey, that's a bit weird. Say my year 11s. Okay, make sure they're not writing y equals infinity x or y equals maths error x. It's a vertical line. And it's astonishing how forgetful they are that they know what a vertical line is. It's just the line x equals 5. But it's well worth doing this because they'll do all sorts of nonsense with 10 over 0. It's not faffing on about infinity. No, it's just the vertical line, x equals 5. It's not of the form y equals mx plus c. So this is x equals 5. Where was our last point? Oh, x equals 5. So our intersection point is on all three medians. And that is always true. That is always true. So the three medians of a triangle always meet at a single point, and that point is called the centroid of the triangle. And you can predict it. So you can work it out, you can guess in advance, you can predict in advance its coordinates, given the coordinates of the triangle, of the vertices of the triangle. And there's a really nice activity. It's quite hard algebraically. I wouldn't do it algebraically, but I'll definitely do it numerically. I'd say to the kids, right, choose three coordinates. Let's get all your answers together, all your different centroids together. Right, can we spot a pattern? Can we see what's going on? And it's kind of the obvious answer when you do it. I'm not going to spoil the surprise, but when you get the answer, you go, oh yeah, that's kind of like what it should be. That kind of makes sense. That's just a better picture of what we've just done. So that's so you can just about see, I hope, you can just about see that they meet at the middle, and where they meet is at the point 5, negative 2/3. Now, what's great is the same thing is true for the perpendicular bisectors. And this is the kind of thing one does sometimes with sort of in year 7, year 8 with constructions. You get your rule and your compass, and you construct sort of, you just do that, don't you? You construct that perpendicular bisector, and then you do sort of the same thing on the other side, and you get that perpendicular bisector, and then you do the same thing, and it never works because they can't hold the compass correctly. But you should discover that the three perpendicular bisectors meet at a single point, and that point is the circumcenter of the circumcircle, i.e., if you expand your compass, you can draw around a single circle like that. And that's quite a hard thing to do with rule and compasses because it requires lots of accuracy. But if it's not something you've done before, it's a great thing to do. And it's a real surprise that you stretch out the compass to reach one of the vertices, and as you go around, with a bit of luck, it meets the other vertex. There it is on for this triangle. So you can see just about, I've found the perpendicular bisectors. So those are all the bisectors, and where they meet is that point there, and that point there is the center. As you can again sort of see, that point there is the center of the circumcircle. Now, that is always true. Again, don't try and prove it generally, but again, so what I would do is I'd take my triangle, and you've got your coordinates. So now we're just working directly with these coordinates. So this line, this side, has got gradient. Well, what is it? We've gone up 12 and across 6. So that's got gradient 2. So I want the perpendicular through the midpoint. So I want gradient -1/2 through the point -2, 0. So it's y equals -1/2 x plus something. Forget that. Let's make it 2y is -x plus something. Well, y is 0. So, and the negative x is +2. So altogether, it's 2y is x take away 2. So that's that one. And then you're going to do the same thing and find where that point is, and then verify with that. Exactly, Doug. This is exactly the center of mass, which might give you a clue what the answer is. So the centroid is the center of mass. So if you teach Key Stage 5, or remember from your own language, your own study of mathematics, then the centroid of a uniform triangle is the center of mass. Yes, absolutely, Claire. So for an obtuse angled triangle, the center of mass is outside the triangle, and actually so is the circumcircle. So the circumcenter of the circumcircle for an obtuse angled triangle is outside the triangle. It's quite a nice point. Yeah. So the centroid and centroid, if you have a uniform triangular lamina, the center of mass and the center of gravity are at the centroid. If it's not uniform, that's not the case, but that's a different matter. Okay, and so so again, just think about the practice, the fluency. They're going to be finding equations of lines, finding lines intersect, but at the same time with the purpose, which is discovering a nice thing that they are concurrent. They meet at the circumcircle. Less well known is that the same is also true for the heights of the triangle, called the altitudes. So if you drop perpendiculars from a side to the opposite, so not bisectors, these are just straightforward perpendiculars from one vertex to the opposite side, they all meet at a single point as well. And again, same activity, find the equations of the lines, find the grade, find their intersection of two of them, find where the third one meets. And they are concurrent at the orthocenter, it's called. And that's my picture here. So you can see here that that's a right angle, that's a right angle, that's a right angle. So those are the altitudes, but they're not bisectors. They're not going through the midpoint of the triangle. They're not bisectors. And they meet at the point 7,1. And then the lovely kind of like twist in the tail, or sort of surprise, is that, so the altitudes for my triangle meet at 7,1. Sorry, 70, not 7,1, 70, sorry. Okay, 70. The perpendicular bisectors meet at 4, -1, which is there. And the centroid was 5, -2/3. Centroid was 5, -2/3. And with a little bit of optimism, you can see that they make a straight line. So the centroid, the orthocenter, and the circumcenter are collinear. And that's always true. For any triangle, they are always collinear. Sometimes they're identical, but not always, but they are always collinear. If you want to prove that, think about gradients. So overall, we're going from 4 to 7 is across 3, and from -1 to 0 is up 1. So we're going across 3, up 1, and from here we're going across 1, up 1/3 to get to -2/3. And obviously they're the same gradient. They've both got gradients of a third. So same argument we had earlier. Gradient parallel lines with a common point, therefore they're collinear. And that's always true. Always true that the circumcenter, the centroid, and the orthocenter are collinear, but don't try and prove it. They're in the slides, Claire. Is that okay? Circumcenter, orthocenter, and centroid, but it's all in the slides, which will be with you later this evening. So lastly, I want to think about lines and circles. So X squared plus y squared is 50. Your kids need to know that that's the center of the circle, center 0, 0, radius 50. So that needs to be automatic. Center 0, 0, radius 50. And so let's think about the line. Okay, so we've got a straight line, y equals 3x plus 10. So let's find out where they intersect maybe. So how are we going to do that? We're going to solve it simultaneously. So let's have x squared plus, so we substitute 3x plus 10 all squared is 50. So what are we going to get all together? Bit of mental algebra. X squared plus 9x squared is 10x squared. We're going to get 3x times 10 is 30, then twice that, the cross term, this will be the AB and the AB. So that's going to give me 60x. And then I'm going to get 100 at the end, and I'm going to take away the 50. So I'll be left with 50 equals 0. Obviously, I expect the kids to write out the same thing. Did I say radius 50? Sorry, radius root 50. Sorry, I must have said radius 50. Sorry. You were all thinking the same thing. Just unmute yourself and shout at me. It's fine. Okay, so divided by 10, x squared plus 6x plus 5 is 0. Factorize x plus 1, x plus 5 is 0. Right, fine. X equals -1, x equals -5. What are the y values? Well, I can work it out. -3 plus 10 is -7. -15 plus 10 is -5. Sorry, -3 plus 10 is +7. And so it looks like that, something like that. Okay, so yeah, intersects in two places. Fascinating. Well, it can be so. Let's try the next one. So again, substitute. So we get x squared, and then obviously y squared is going to be x squared plus 20x plus 100 is 50. So I'm going to get 2x squared plus 20x plus 50 is 0. And so x squared plus 10x plus 25 is 0. So factorize x plus 5, x plus 5 is 0. So the answers are x equals -5 and x equals -5. Ah, right. And this is what I was getting back earlier. So the algebra gives us the answer -5, -5 twice, the repeated root. How can that be? How can a line intersect a circle only once? I mean, does it just go into the circle and stop? And of course, the answer we know is a tangent. So the answer you're trying to draw out from the kids, you remember, get the maths from them. You've got to sort of, I do this sort of feigning ignorance. How can this be? How can a line intersect a circle? How can a line cut a circle? And I used the wrong words deliberately. How can a line cut the circle twice? Sorry, once. It goes in and goes out again, surely. And you want them to go like, no, it doesn't cut it. It touches it. It slides past it. It's the tangent to it. And then obviously the third case, well, you can see what the third case is going to be. The third case is going to be missing it completely. So what's going to happen? Well, now when we do the algebra, we're going to get x squared plus, so for the third one, 9x squared, take away 150x, and then plus 625, take away 50, so plus 575 is 0. So we're going to get 10x squared, take away 150x, plus 575 is 0. Okay, don't fancy factorizing that. Let's use a quadratic formula. What's going to happen? They're going to get x is 150 over 20, add, subtract, and they're going to go, I can't do it. And why can't you do it? Because you're going to get a negative number. So the algebra of I can't solve the quadratic equation is the geometry of the line doesn't intersect the circle. And that's what I was trying to say earlier about the fluency quadratic equation. Just look at all the fluency, all this expanding, factorizing, rearranging. There's a lot of fluency happening here. There's the fluency of the quadratic equation and the geometry, the understanding of what that means. So no solution algebraic means no intersection geometric. And that's what I mean by bringing the two of them together. Look at my last couple of slides, if this is okay. If you need to go, please go. I'm still recording, so you'll be able to get this, but I've got another couple of slides, if that's all right. So the same idea, but almost sort of working backwards. So now I'm telling you it's a tangent. What's the value of m? So it could do a bit of trial and improvement, could do a bit of messing around. This link, by the way, at the bottom is a link to a Desmos thing I think I put in the cloud. I don't really know how Desmos works, like sharing, but it said click here to share link. So I think this is a picture you can look at yourself, and there's a slider, so you can slide the value, you can change the value of m and see what happens. I'm not sure you might need a Desmos account to do so, but it's free. So there's a link here worth following, I think. So what's going to happen algebraically? Well, we're going to get x squared plus, right, m squared x squared, take away 10mx plus 25 is 20. Now that, yeah, I'm not expecting the kids to do this in their head. They should be writing something out. And so we've got 10mx, and then we've got 5 there is equal to 0. And this is really hard, I find. This step to go, well, what have you got here? They'll say 2x squared or something. No, we've got x squared 1 plus m squared. And get them to realize that the coefficient of x squared is 1 plus m squared. This is the a. This is the a in the quadratic formula, and that's the b in the quadratic formula, and that's the c in the quadratic formula. And that will really throw them because they're not used to it certainly not being a number. They'll say it's 10, but the idea that it's a number and something else is 10 and m. That's the coefficient of x. But it's productive struggle. It's desirable difficulty. It's worth struggling through. Because what are we saying? We're saying it's a tangent. So if it's a tangent, what we want is there to be only one solution. But how can that be? Because when I solve this using the formula, what happens is I get 2 solutions. I get plus or minus. I get 2 solutions. So I'm not going to get one solution for the tangent. This is me feigning ignorance for my class. How can I get one solution? Okay. Can I come back to that point in a moment, Claire? I don't disagree, but can I come back to that? Thinking about sort of, yeah, how would I want only one solution. How can that be? Well, that can only happen if there isn't a plus or minus in the first place. Actually, what I'm doing here with the plus or minus is plus or minusing 0. And so what I need is that bit to be 0. So what I need is the 10m squared, subtract 4 times 5 times 1 plus m squared to be 0. And so I've got 100m squared, well, take away 20m squared, I've got 80m squared, take away 20 is 0. And so I've got m squared is a quarter, so m is positive negative a half. At which point I get out my Desmos and I solve, and I say, look, we were right. Phew. Or even do the Desmos first and say, look, it looks to me from the slider, like m is a half. Let's see if that works. Because if you know where they're going, they know they're heading towards m equals a half. In fact, what you could do, you see, you could get the m equals half from Desmos, positive negative a half, and then test it in there, and then realize that gives you the plus minus 0. The reason why it gives you a tangent is because when you then solve, this equation will become x squared, it would be 5 quarters, and then that would be 5x, and then that would be 5. So when you solve that quadratic formula, you would get the discriminant being 0. You go, oh right, that's because there isn't a plus minus. And then my last slide is the same thing, but just working out with the k. So the same idea, but working out with the k. All I'd say is, Claire, I understand your point completely. Interestingly, of all the activities on today's slide, I have actually done this one quite recently. I was doing some cover work with some high attainers in year 11. They wanted some stretch and challenge for the high attainers, and I did this with them. And yeah, they found it hard. They couldn't do it by themselves, but they could all the stages. They could construct the stages through my questioning. And then, of course, once I've done one, then they could have a go by themselves. So this is very much get the maths from them. You know, what do you notice? What do you think? What do you predict? What do you expect? And you are leading them through the argument. You're not expecting them to come up with the argument, but your careful questioning, I think, makes it accessible. Yeah, cold, absolutely agree with you completely. But I, yeah, having done this, I do think it can work. But yeah, it was a slog, but they liked it. They were really excited by the idea of being able to kind of make these sort of predictions. And absolutely, you could use it with year 12. I'd expect more fluency by themselves. And in the end, what's the point? The point is not to teach them how to find the value of m. The point is to get them to connect. If you know it's a tangent, which is a geometric fact, that forces an algebraic fact about the quadratic equation. And that's the point, really. The value is kind of irrelevant. The point is that something about the geometry is telling them something about the algebra. And that's the idea you want to try and bring together. So And yes, so I keep wanting to stop, but you keep asking great things in the chat. So Doug, absolutely, if you complete the square, it's really nice. So what happens when you complete the square? I mean, obviously, you've got to get that. You've got to have the 0 in there somewhere. So, well, obviously, folks, please go if you need to. I'm just going to do this complete the square, but I do realise I'm way overrunning, which is quite ironic because I was complaining this morning. I was in a meeting this morning. I was complaining about it overrunning. Hypocrite me. So I'm just going to do the complete the square if you want to stay and watch it, or stay and contribute to it. So what happens when you complete the square on this? Well, I would multiply through by 4 and divide through by 5 first, tidy it up first. So divide by 5 and then multiply through by 4. I get x squared, take away 4x plus 4 is 0. So I get x take away 2 all squared. Job done is 0. So x take away 2 is 0. So x equals 2. So when you complete, so again, when they complete the square on it, then they see straight away that there is a unique solution. So anyway, I've changed x to n rather unhelpfully. Okay, I am going to pause there. I'm very happy to take some more questions if you want to, but I also want to make sure people feel they can go without missing out on anything. So thank you very much. I'm sorry I've overrun. I think there's some difficult fluency in here, so keep an eye on the purpose, which is to make the connections with the geometry, to help them see that deeper level of understanding. That's what we're trying to do with our higher attainers, make them look deep, not superficial. Okay, I shall pause. Bye for now, folks.